Hello science people, just making a quick video for you linking the electron configuration stuff that we were talking about to the periodic table and some of the different groups on the periodic table that you'll need to know. So let me just flip my laptop around and I'll get started taking some notes. Okay, so what we've got here is just the IB periodic table. Now, some of these groups should be familiar to you already. So, for example, this column here, and there's a special reason why I'm highlighting that one so thoroughly. Let me just switch to a green pencil. This group here are called the noble gases. And they're called noble gases because they're snobby. They don't react with other elements unless you basically do the most reactive things that you can think of. Noble gases are unreactive. And because they're unreactive, they're actually really hard to identify. These elements were some of the very last ones found, other than the guys down the bottom that scientists created. These noble gases were discovered super late simply because we don't find them in compounds. If you are any other element on the rest of the periodic table, your entire aim for every chemical reaction you undergo, every time you gain or lose or share an electron, your aim is to end up getting an outer shell that looks like a noble gas. So what do I mean by that? Why is that not erasing? Okay, so what do I mean by that? Let's look at fluorine and work out its electron configuration. So fluorine has 9 protons, which, because we're talking about atoms, means it's got 9 electrons. I say atoms as opposed to ions. So my first shell can hold 2 electrons, which means I've got 7 left over, which the next shell can hold. So fluorine here has an electron config of 2, 7. Now, to get a full outer shell, let me switch to that. To get a... Why is this not letting me? Okay, never mind. To get a full outer shell, fluorine can either gain 1 electron and look like neon, or it can lose 1, 2, 3, 4, 5, 6, 7. Put that in terms of effort. Which one of those is going to require more energy? Does it need more energy to gain 1 electron or to lose 7? It takes a lot less energy to gain 1 electron than it does to lose 7. So fluorine, so let's look at the outer shell, just the outer shell of fluorine. So that's 7 electrons. So it has 1 spot on its outer shell that needs to be filled. So fluorine is going to want to gain 1 electron and end up with a 1 negative charge. Let's now look at chlorine, who's fluorine's older brother. So chlorine is just below fluorine. So chlorine has 17 protons, that's its atomic number, and 17 electrons. So 2 electrons go in the first shell, which means I've got 15 left over. Then 8 go in the next shell. So 15 minus 8 gives us 7. And then I've got 7 in the last shell. Let's now draw out this same dot structure that I've drawn on the right for chlorine. So chlorine has 7 electrons in its outer shell, which means it's got space for 1 more. So chlorine will want to gain that electron and get a net minus charge. So looking at those two guys, now that they're these ions, so this is called the fluoride ion, and this is the chloride ion. These guys now have full outer shells. So those are now happy. Hopefully you see that the way these two elements reacted is really similar. Both of them needed to gain 1 electron in order to get that full outer shell. So fluorine and chlorine, and in fact this whole row of elements here, react in really similar ways. Oh, I didn't mean to delete that green. Give me just a second. So we've got our noble gases that are all unreactive. Next door to them in group 17, some old-fashioned periodic tables you look at might call this group 7, but this next group is called the halogens. These guys, particularly fluorine and chlorine, can be quite reactive, and they're quite good electron stealers. Let's jump to the other end of our periodic table now and look at these guys here. Now, there is a reason I've skipped hydrogen, and that's because hydrogen's a bit weird. I might actually pop that on the end of this video. So, these guys here, let's start with the electron structure again. So let's start with lithium with 3 protons and 3 electrons, and sodium, which is 11 protons and 11 electrons. The reason I'm not drawing out the protons and neutrons for these guys, remember they're locked away in the nucleus, which is right in the middle of the atom. Chemical reactions only mess with electrons, not with protons and neutrons. So let's start with lithium. We know that lithium can take 2 electrons, sorry, I didn't mean to draw that. Lithium can take 2 electrons in its first shell, then there's 1 left over. For sodium, it can take 2 electrons in the first shell, 8 in the second, and then there's 1 left over in the third. If you want to confirm you've done this correctly, all you need to do is 2 + 1 = 3, which is the same as that. 2 + 8 + 1 = 11, which is the same as there. Okay, so let's draw that in the dot structure. So we're just looking at that outer shell. So lithium has 1 electron in its outer shell, and so does sodium. So in order to get that full outer shell so it looks like a noble gas, lithium can either gain 1, 2, 3, 4, 5, 6, 7 electrons, or it can lose 1. Again, which do you think is going to take less energy? It's a lot less energy to lose 1 electron than it is to gain 7. So what lithium will tend to do is it will form a lithium plus ion, and sodium will form an Na plus ion. So when lithium plus forms, it has 2 electrons in its outer shell, so it looks like helium. We call that being isoelectric. So I defined the prefix iso when I talked about isotopes in class, but isoelectric, there is a slightly different biological meaning to this term that I will explain to you if you do chemistry and if we do the biochemistry topic. So iso means same, electric in this case means electrons. So the same electron structure. So Li plus has 2 electrons, so it looks like helium. Na plus has 10 electrons, so it looks like neon. This idea that atoms want those full outer shells, that the noble gases is what we want, that is called the Octet Rule. However, again, if you study chemistry with me next year, I will explain to you that it's really more of a guideline. So, hopefully you can see that the elements on the left-hand side of the table are going to want to lose electrons, and these guys on the right-hand side of the table are going to want to gain. And I know I circled my noble gases in there, but I couldn't be bothered trying to draw around them. However, let's zoom in a bit and look at carbon. So just carbon sitting in here on its lonesome. Now, carbon is a super important element when it comes to biochemistry, so the chemistry of living things. So carbon, sorry, I'm just trying to work out my scaling. Carbon can either gain 4 electrons or 1, 2, 3, 4, lose 4 electrons. Now, both of those require quite a lot of energy. So carbon actually gets its octet in a slightly different way to things like halogens and things like this pink group here, which are called the alkali metals. So next class, I'm going to talk about how carbon and other elements like carbon in the middle of the periodic table get those full outer shells, how they get that octet. Thank you so much. Have a great rest of your day. I am, of course, available to answer any questions you've got, either by leaving a comment on the YouTube video or by sending me an email. Thank you so much. Have a fantastic rest of your day, and I will see you next time. Bye.